introduce you quickly.
Okay.
The audience, we have Professor Anand Kumar Jha today from the Physics Department, Indian Institute of Technology, Kanpur. He did his PhD from University of Rochester, and then he also did a postdoc there, and then eventually he worked as an integration engineer in Intel Corporation. And finally, he joined, I think, 2013 IIT Kanpur, and he is a full professor now. So his research interests now include quantum optics, optical coherence, quantum entanglement, quantum metrology. And today he's going to talk about a very interesting topic, quantum superposition, entanglement, and quantum technology. So, I mean,
okay.
to give you,
should I?
Yes, please.
Should I share my screen?
Yes, please share. Yes.
So, can you see my screen?
Yes, it is fully visible. Thank you. Yes.
Okay. So I'll get started. So again, thank you so much for the invitation. It's always very nice to present in this one, which has been going on for this is the 4th international conference on this one. So the topic that I have is very at the tutorial level, and at the end I will just maybe talk about maybe in 5-7 minutes some of the things that experimentally we have been doing in my lab here. But mostly it will be very aimed at the undergraduate level. So if it's a very tutorial level talk that I have prepared. So the title is Quantum Superposition, Quantum Entanglement, Quantum Technology. Okay, I'm Anand Jha from Department of Physics at IIT Kanpur. And here is just a quick outline of the talk, very simple. 2 things that I will discuss in detail: quantum superposition and quantum entanglement. And in both of these, I'll spend a lot of time on the basics. In quantum superposition, I'll kind of also talk about how different it is from classical superposition and other aspects. And then some technology and application that actually comes out of this fact of or this property of superposition in quantum mechanics. In entanglement part also several basic stuff, and then also are there classical analog, and then some application that we have also been working, and then some applications which are that everybody is working on, very globally identified kind of goals for the next generation technologies. So again, I don't know what is the format of the talk is, but I am fine being interrupted anywhere. And again, depending on how much time I have, apart from the questions, I can shorten or the talk accordingly. So yeah, feel free to stop.
Typically, we are looking at like 45 minutes, but then we are flexible. And like your talk being at the tutorial level, it will be very useful for all of them. And I mean, if you can take question at any time, then that will probably be very helpful. I mean, yes.
Yeah. So yeah, I am perfectly fine. In fact, I would like that more if interrupted in between with all the questions. So
thanks.
Okay. So let's get started. So first, just what is the basic difference between classical and quantum mechanics? I mean, again, most of you, many of you probably already know all of this, but this is thinking of the UGs that have that are part of the audience. So one of the main difference and the differences that I'll point out, they are not all independent; they're kind of interconnected, but still, it's useful to look at it at separate bullet points. So equation of motion, that's very different in classical as versus in quantum. So in classical, when we talk of the equation of motion, the equation of motions are always in terms of real variables such as position. Let me just take the pointer. Such as position, momentum, like Newton's equation in terms of position, momentum, Maxwell's equation in terms of electric field. So these are all real variables: electric field, position, momentum, and so on. But in quantum mechanics, the equation of motion is in terms of a very abstract mathematical quantity called wave function, and which is a Schrodinger equation. And this psi is the wave function. Psi apparently contains all the information, but psi by itself is a very abstract mathematical quantity. So that's one difference. Here you have real variables. Here you have some abstract mathematical quantity as part of the equation. The second is the determinism. In classical mechanics is in principle deterministic, that if you know everything at t equal to 0, you can predict what is going to come out at some other time t. But quantum mechanics is even in principle indeterministic. And the one way to say see this is that, you know, in quantum mechanics it's not even possible to you know, exactly figure out or specify all the initial conditions very accurately. So the one way you can see this, just one example in which you see the indeterminism is let's say you have a light source falling on a double slit. I'll do a lot of double slit in this talk, so that's why I'm keeping this as an example. If you have a light falling on a double slit and then passing that and falling on a screen. Now, where this photon, well, before hitting the screen, it has the possibility of, you know, falling onto the screen anywhere. But eventually it hits the screen somewhere. And where it hits the screen, this cannot be determined. This is even in principle impossible. And that is what we mean when we say that classical mechanics is in principle deterministic, but quantum mechanics is not. So this actually has an application, this intrinsic indeterminism in quantum mechanics, that actually has a very nice application, and that is in terms of generating quantum numbers, or generating string of, you know, numbers 0 and 1, and that string is completely random. So for example, if I have a photon or a chain of photon, a string of photon falling onto a beam splitter. A beam splitter is a device that splits a beam into half. Part of this goes this way, part of this goes this way. But if it's a photon, the energy cannot be divided, so the entire photon goes either this way or that way. So the beam splitter effect only comes in the fact that if I send n photon, on an average n by 2 will end up here, n by 2 will end up here. But which one of those end up in that side, that can never ever be predicted. So when the photon falls here, if that is called 0, if it falls here, that's called 1, then this generates a string of 0 and 1, which is truly random. The string that one generates through classical algorithm eventually repeats after a while, but one that we have here, that will be truly random. So that's actually one very important application, just from the fact that it is totally truly indeterministic quantum mechanics. The other is the effect of measurement. In classical description, an act of measurement does not affect the system, but in quantum mechanics, well, it does affect the system, except there's one exception, and that is when the system is already in its eigenstate. But in general, if you have a wave function psi, if you make a measurement, it can collapse into all the possibilities that it actually has. For example, this is, again, I'm taking the screenshot from a real experiment done with single photon, Young's double slit experiment. Now, these dots, if you can see, these are the pixel on a camera where the photon has hit, at least some 40 pixels, 40 dots. The number of pixels are 512 or 512. So where this one hits is completely random, but you have the exact same state that is actually falling on the camera screen every time. But where exactly it falls, that cannot be determined. So and once the measurement has happened, the photon is gone. It is not there. So in this case, the measurement has completely destroyed the system. But in general, it need not completely destroy the system, but it definitely changes the system. Of course, the exception is when the system is in the eigenstate of the measurement operator. And this one example I can show is if you have if you know that the incoming photon is either horizontally polarized or vertically polarized, and if we are using a polarizing beam splitter as our measurement detector, then if the photon goes this way, then we know it's vertically polarized. If the photon goes this way, then we know it's horizontally polarized. So here, if it's a vertically polarized, it will go this way. There is no confusion. So here, even if you know, this act of measurement doesn't change the system because it is already in one of the eigenstate. The other difference is the duality. This is almost the crux of quantum mechanics. The classical mechanics, there is no duality. A system behaves either as a particle or a wave. There is no confusion. If it behaves as a particle, we use Newton's equations to describe it. If it behaves as a wave, we use Maxwell's equation to actually describe it. But in quantum mechanics, we don't have a particle or a wave. We have a system, and that system can behave as wave and particle at the same time. And this wave-particle duality is the characteristic feature of quantum mechanics, would say. And of course, so if it is particle, Newton; if it's wave, it's Maxwell. But if it's both, then how do you describe it? That's the Schrodinger equation, which of course describes the simultaneous existence. Again, this simultaneous part is very important, that it is not that it is sometimes wave, sometimes particle. It is both all the time. It is just that we cannot manifest both at the same time in any experiment. It is one, when it is, some experiment reveals wave, some experiment will reveal particle, and the experiment that reveals wave part more cannot reveal the particle part as much. And that's also called the Bohr's complementarity principle. The last one I have in my list is the superposition principle. Superposition happens very differently in classical mechanics versus quantum mechanics. So in classical mechanics, typically superposition yields a definite new state. But in quantum mechanics, superposition does not yield a new state. It just changes the probability that the system can be found in those basis states of which it is a superposition. So for example, here, the superposition of horizontally polarized or vertically polarized light with some coefficient AB, it only means that if I go and detect, I'll always find the photon to be either horizontally polarized or vertically polarized. But if it's a superposition state, that means I have A square, mod A square is a probability that it is here, mod B square is a probability that it is horizontal. Okay, but yeah, so superposition is very important. So and I have some demonstration also to actually illustrate that. One very essential, this I will stress several times, but one very essential difference that we can not visibly see, but the way we can convey is that in the classical mechanical description of interference, it is all based on dividing the field amplitude, and dividing the field amplitude necessarily means dividing the energy of the field. But in quantum mechanics, the description of interference is based on division of wave function. So here is field amplitude, electric field amplitude, here is a wave function. But unlike division of wave amplitude, wave amplitude, the division of wave function, it does not imply division of energy. Since the minimum energy is a photon, and photon cannot be divided any further. This part I kind of want to explain in more detail along with wave particle duality. So I just have a next few slides through this picture. I'll try to kind of explain, and then I'll also show you some experimental results, not simulation, real experimental results, the video of that, to kind of convince you how interference is different in classical versus in quantum. So this is a very simple situation. I have a light source. It falls on a single slit. This is class 11-12 stuff, and falls on a screen. So what is the pattern on the screen? Well, it will be the Fourier transform of this single slit, and that will be and that way we can calculate the intensity on this screen. Right now, I just have a one-dimensional slit over here. Okay. Now the question is, if I reduce the intensity of the source, what happens to this pattern? Well, if I reduce the intensity of the source without doing anything else, that means the slit size and the slit the separation from the screen, if everything remains same, then we'll get exactly same pattern. The functional form will be exactly the same, except the overall intensity will decrease. That's the only thing that will happen. Then now, if I reduce the intensity even further, then what happens? Well, then the overall intensity will decrease even further, but the overall pattern, the functional form of the pattern, that remains exactly the same. Well, if I reduce the intensity even further, then what happens? Well, if I reduce the intensity even further, then you can just continue. I mean, every time just the overall intensity kind of decreases, but the functional form of the intensity pattern remains the same. But there comes, so classically, if you're trying to describe it, this will just continue. No matter what the level of energy, how small, how low the intensity, it is always the same functional form of this pattern. The only thing that happens by reducing the intensity is that overall intensity gets reduced over here. But what happens in reality is that beyond a point, if you reduce the intensity, then you will start seeing these dots. Of course, the camera that sees this will not be able to see this. So once you see nothing here, you need to bring in a new camera, which has a single photon sensitivity. And if you do, then this is the kind of pattern you will actually see. So this is the dot pattern. This is, nothing compared to this. So this is just the pattern of dots. Maybe the density of the dots is contains as to what the intensity of light was on these planes. Now, if I reduce the intensity even further, then I will end up with just a few dots. And here you can't even say that the density of dots are the same as the functional form. There's no way of seeing any functional form over here. So this is what happens. So up to here, you can explain it classically. But what happens, at this level, intensity level, this cannot be explained classically. Next, I put another slit, and that becomes the Young's double slit experiment. In this is a bright and dark fringe pattern. This we know. Now, if I reduce the intensity of the source, what happens? Well, it is the same fringe pattern. The contrast is exactly the same, except the overall intensity has reduced. Reduce the intensity even further. Maybe I hope you could see it. The functional form of the fringe pattern or intensity pattern is exactly the same. It is just that the overall intensity has reduced. So classically, if I just keep reducing the energy, or if I keep reducing the energy, classically, this is what I will keep predicting. That same functional form of the intensity pattern, but the reduction of overall intensity. But what actually happens is this. So after a while, I'll see that I have this dot pattern. And of course, the density of dots. So for example, here it's more, here is almost nothing, more, nothing, more, nothing, and so on. So the density of dots is actually equal to the overall pattern, the functional form of the intensity pattern that I get. But what I have is not a continuous distribution of intensity, but it is a dot pattern. Reduce the intensity even further. Now I cannot see the pattern, but of course, what I see is that, yeah, these are individual dots. So from here on, you cannot describe it classically. You have to describe it quantum mechanically. So this wave particle duality and this interference that we are talking, this basically brings us age-old question: what is light? Is it wave? Is it particle? And the answer is it is both. And it is both at the same time. Now, if one thinks about it, when we think of wave, it is something completely delocalized. If you think of particle, it is something completely localized. So what we are essentially saying is that the light is something which is wave as well as particle. That means light is something which is delocalized as well as localized. Or another extreme way of saying is light is something that is everywhere and somewhere at the same time. This is so nonsensical that something can be everywhere and somewhere at the same time. But this is what it is. This is the state of quantum mechanics at this point, and that's how we kind of understand it. Very nonsensical, but this is what it is. So as far as interference is concerned, if I compare the classical and quantum, in the classical, we have division of amplitude. This division of amplitude means division of energy. And the superposition of amplitude gives me interference. In quantum mechanics, we have division of wave function. That cannot mean division of energy. And of course, the superposition of wave function gives me interference. So the classical description is fundamentally incorrect, but it definitely works at high light level. So we use it all the time. But this becomes inadequate in those slides that I was trying to show. It is inadequate at single photon levels. But the quantum mechanical description, it is fundamentally correct at all level, whether low light, high light. But since the math involved is little difficult, so people mostly use it at high light, at single photon levels. But there are, if there are quantum effects at high light, you have to use quantum description and not classical. So it is fundamentally incorrect, but at a high light level, one can use it. but this is fundamentally correct at all light levels. So then, given this situation, how does one describe single photon interference? This is best way is in terms of Dirac, that each photon interferes only with itself. Interference between two different photons can never occur. So this is a very almost nonsensical statement, but this is the best description that one can have of interference as we see in quantum mechanics, or as we see in real lab, at low light level. And again, from the duality, more we know in any particular experiment, the more we know about the particle nature, or any experiment that reveals more of a particle nature, the same experiment will have less revelation of the wave nature, and vice versa. And that's the Bohr's complementarity principle. Okay, now at this point, I was just showing simulation. Now this one, I just want to show something real. So this is just a Young's-double-slit experiment. At high light level, you see this as a fringe pattern, but I want to show this is the actual, I'll play a video. This is the actual I can. Okay. Right. So this is the experiment, and this is the sketch of the experiment. This is my camera screen, and this is the photograph or the video of the real camera screen that we have used. And then we are sending photon one by one.
Sorry, we see black screen.
You see completely black. Yeah, for now it's completely black. Half of the screen is black, right?
Not fully.
Complete screen is black.
Yes.
You see that right-hand side is completely black.
No, that's fine. That is the whole idea. Yes. So now I will play because it is completely black, and now you will have the photons falling onto this. So let me just stop the music. Now, if you see, you have this dots appearing,
coming up. Yeah. Yes, very nice. Yes.
So these are the real single photons. This is taken in the lab. So this you can see, you cannot really see any pattern right now. This is completely random. Of course, we know what pattern will actually emerge after a while, but at this point, it is completely random. The size of the dot that you are seeing is actually size of the pixel of the camera, which is about 16 micron by 16 micron. So now you see more dots appearing. That's because this experiment was taken over 1 hour, but I'm showing you like a 1 minute version or 1.5 minutes version of this. So now you see there's a lot of accumulation of these dots happening over here. If you look at the density of the dots, that is starting to resemble the fringe pattern over here. But even at this level, these are just dots. This is not a continuous distribution of intensity. So of course, now you don't see the individual dots coming in because now we are, again, as I said, this was done over 1 hour, but now the frame rates are pretty fast. And so if I continue, let me stop here. Right. So now you see very nice fringes, very clear fringes that actually have appeared, but these were built from photon by photon, and that is the whole point. These were built one photon at a time, and even at this level, you can see these are individual dots, but now I can see the whole intensity pattern as well. And this cannot be explained classically. This simply cannot be explained classically. Okay, so, well, I have some more simulation, but maybe I can skip those. Maybe I can show this. This is a stick figure. This is some simple figure. We're just doing it for fun. And this is about 10,000 photons. Of course, this you do see a dot structure, but there's some, it's not that perfect dot because our idea was a little different here, which was that we wanted to make photon dance. So this is about 10,000 photons, making this stick figure. And I can stop the music. And we have a little bit. Okay, so well, this is just for the fun. I show it to undergraduates just to kind of convey this, that doing quantum experiment is actually fun. So this is about 10,000 photons, and then you're kind of changing the pattern and making them kind of dance. So this is just for the fun part. Okay.
Oh, wonderful. Very nice.
Sorry, what was that?
This is wonderful. I mean,
Oh, thank you.
yeah, it's very nice. A lot of very interesting. How did you generate that?
So all you require is an aperture. So of course you cannot make that as a hard aperture. So there's an electronic device called spatial light modulator. So on which you can make any aperture that you need. So we make an aperture, which is the Fourier transform of this pattern. And that we put on that SLM. And we record the intensity of the far field. And this SLM will then also change this pattern. At least we were changing the pattern 10 times a second. So for different pattern, it's just 10 times a second. It plays continuously, looks like a video. So that's how we actually do it.
Very nice. Very impressive. Okay.
So, okay. So continuing, well, this is another one.
Excuse me. So
yes.
Why that figure is in red in color? Like, are you sending the photons of particular frequency something?
No, this is false color. This is
Fluorescent.
This is false color. This is color is false. Just to make it appear. Look,
Okay.
This is just for the fun part. Yes, it is. Although we were using the helium neon laser, very kind of intensity reduced helium neon laser, so that was red. But my camera is basically not the color sensitive. It only gives grayscale, the EMCCD camera. So but this is just a false color. Yes.
Yeah, but like single photon, you mean like it will be multi-mode only, right? It won't be a particular frequency of.
So helium neon laser, whatever bandwidth it has, it definitely has some bandwidth. So it will be within that. That is correct.
Okay.
Okay. I will skip this. Okay. So now maybe something about quantum measurement. So measurement is a very important aspect in quantum mechanics, and that is what, as I was saying, that is what makes it different from classical. And whether it is whether it is falling wave particle duality, measurement has to come into picture. We have to bring in for example, a screen for the Young's double-slit experiment to be able to see this dot pattern. And when we have this dot pattern and a fringe pattern emerges from that, that is something that cannot be explained classically. So many times, if you don't have measurement, and if you just see the wave effect, that can always be explained through wave mechanics, and you don't require quantum mechanics. So wave aspect combined with measurement, which truly reveals the particle picture, that becomes the complete quantum mechanics. So how do we understand measurement in quantum mechanics? I will be very quick on this one. So measurement in quantum mechanics is always associated with a basis, and that with a measurement device. And of course, measurement is very important, because through measurement only you can know anything about the state, because as it is, we know nothing about the system. System is just a wave function, which is a black box, an abstract mathematical quantity. And through measurement, we try to reconstruct, or we try to find out, we try to measure what the state actually was and what was the dynamics of that state. So the measurement basis could be, for example, horizontally polarization, and in the polarization you can have horizontal polarization, vertical polarization as the basis. And if I have that, then this could be my detector, just a polarizing beam splitter. Now, polarizing beam splitter, if a vertically polarized photon comes, it will send it this way. Horizontally polarized photon comes, it will send it that way. So that's the measurement device for polarization. So you can also have polarization measuring device in 45 minus 45, which is basically the same polarizing beam splitter, but rotated by 45 degrees. In the position basis, the detector that we have is any camera and the pixel can be the position basis. If you want to measure momentum, what we typically do is that we have a lens, and on the focal plane of a lens, we put a camera. And then when we detect the position location on the camera, that essentially gives us the momentum of the state. So now measurement, as I was mentioning, that unless the system is in one of the eigenstate, measurement actually changes the system. So if I want to know what the system is, know what the state is, then and if it is in one of the eigenstate, then only one measurement is actually required because we already know everything about that state. So suppose here I have a state of the photon which is vertically polarized, and if I'm using a polarization detector, then it is in the eigenstate. And so if I make this measurement, then each time I will get exactly the same value. Vertical, vertical, vertical. No matter how many times I repeat the experiment, I'll get exactly the same value. If the state I know is another eigenstate, let's say horizontal, and if I do the measurement, each time I'll just get the horizontally polarized light. Even if the state, let's say here is 45 degree, which looks like a superposition, but if I have a measurement device, which is in the this rotated basis 45 minus 45, such that this H plus V becomes actually the eigenstate of this measurement device. And again, in this case, every time I make a measurement, I'll get 45, 45, 45, no confusion. But if the state is a superposition state, from the perspective of the measurement device, then if you make a measurement, then it will be completely random as to which basis state it actually shows up. So for example, this is the superposition state. If I make a measurement on several photons one by one, then sometimes I'll get a V, H, V, H, V, V. There's just no pattern here. It's completely random. And by doing n number of measurements and almost like infinite number of measurements, I can then reconstruct what is alpha squared, beta squared. If I want to actually find out the phases of alpha and beta, then I need to set up an interferometric measurement. So that's how measurement works in quantum mechanics. So this two particle measurement, maybe I can skip here. Okay, so now this concludes the quantum superposition part as seen from as seen from one particle perspective. Now I go to the second part of the talk, which is quantum entanglement. Now, entanglement, this is a very cartoonish picture. This is of course not correct, but conveys the idea to some extent. So if two particles are entangled and if you disturb one, both of them will actually get disturbed. And that is the inseparability one talks about, and that this inseparability is the essential criterion for entanglement. Of course, Einstein, Podolsky, Rosen did not like this. And what they then pointed out that this seems like a very disturbing feature in quantum mechanics, and that might mean that maybe quantum mechanics is not complete. So they wrote a paper in 1935, and I'll just produce the gist of it. So suppose I have a diffracting wave, just a wave coming in plane wave, hitting this slit within almost no width. So you have a diffracting wave like this. We can also have just a plane wave with a fixed direction or momentum. Now, from the basic quantum mechanics, if you look at the state here, the position is fixed, but momentum is completely random. And then we can say the uncertain position is 0, uncertain momentum is infinity. On the other hand, for this, momentum is fixed, just one value P naught. Position is completely uncertain, and that's why delta P is 0, delta X is infinity. So that's how the basic quantum mechanics works. And in general, if you put it all together, then we have the Heisenberg uncertainty principle, which essentially says that delta X, there is uncertainty X, uncertainty P, and this product can never be less than h bar by 2. So this is the basic first quantum mechanics. Now, what EPR in 1935, what they showed, they constructed a system of two entangled particles. This is mathematical work. They assume that, okay, let's say the state of the two particles is given by this wave function x1, x2, where x1 is the variable corresponding to particle 1, x2 is the variable corresponding to particle 2. And then they say, let's say we can write the state like this. Now, what is the state? This state is corresponding to particle number 2. The state corresponds to particle number 1. Now, if you look at the wave function, this one, e to the IP x1 by h bar, this is the wave function of a free particle with momentum p. This is again quantum mechanics 101. If I look at this, this is a momentum, this is a wave function of a free particle with momentum minus p. So what do we have here is that we have a state when the particle 1 has momentum p, particle 2 has momentum minus p, and then the state, two particle state is a superposition of several of these states. And that's why this integration. So these first one can have any p value because there's an integration in p. But if the first particle has momentum p, the second one has to have momentum minus p. So that is the state. And if I translate the statement mathematically, then what we find, if we make a measurement on the momentum of the first particle, then the uncertainty in the momentum of the second particle is actually 0. Okay, so now same state by just doing these basis transformation can be written like this as well. Now this is exact same state. Now, but when we write it like this, the way we can interpret is that this is the wave function corresponding to a particle located somewhere. Here it is x1. This is the wave function corresponding to a particle or second particle located at x plus x naught. So again, the first particle could be anywhere because this is finally a superposition of all that. But if the first particle is at x, then the second particle is at x plus x naught. Okay. So again, if I measure the first particle and then ask what is the uncertainty in the position of the second particle, it is actually 0. So of course the state is inseparable. And if I put this delta x conditional, delta p conditional, this is actually 0 in this case for this example. So this is of course less than h bar by 2 and it violates Heisenberg uncertainty principle. And this was the thing that was pointed out by EPR in 1935, that this seems in contradiction with this, then hence there is something wrong with quantum mechanics. And then the question is, quantum mechanics even complete? They said maybe we can have an alternative theory, which with some additional hidden variable, which can explain all that in a more consistent manner. So well, after that, this actually, what they pointed out, this actually has become how one understands entanglement. So if you have this kind of feature in position momentum, we call it position momentum entanglement. You can have time energy entanglement. You can have entanglement in angle and orbital angular momentum. I'll skip this part. So these are all called continuous variable entanglement. You can also have polarization entanglement, which is discrete two-dimensional entanglement. Here, of course, you have to have a state which is inseparable. So if I, let's say, write a two-photon state like this, two-particle state like this, which HH plus VB, you cannot, this is the first particle, second particle, first particle, second particle. This state cannot be written as a product of the state corresponding to first particle times the state corresponding to the second particle. So this is inseparable. But how, in what sense do we see the entanglement here? So, I mean, here it was that the uncertainty product violates the Heisenberg bound, that is entanglement. But in the discrete case, what is the best way of visualizing what is entanglement? So this, I just want to present, I will not do it mathematically. I just want to present it in a very kind of pictorial way. And this pictorial way actually was based on the ideas of this hidden variable, because when Einstein Podolsky rose and they suggested that maybe there is an alternative theory based on hidden variable, people actually worked out hidden variable for quite some time. So I want to kind of illustrate polarization entanglement in terms of the hidden variable arguments, so that we can also understand why it cannot work. Okay, so the way I have it is to the question of what is polarization entanglement is as follows. So I have these two photons and I make some measurements on these two photons. And then I have two models to actually explain the measurement outcome that I have in the experiment. So first is that I will assume these two photons are entangled and then try to explain the measurement results. The second is I will have a hidden variable model. The way it is that I have two independent sources, but there's they can have as many rules as possible in between them, but these are two independent sources. And then we'll see if this model can explain whatever outcome I get, or this can do, or maybe both can do. So very simple measurement outcome that, let's say, I have in my lab is that if I detect the first photon, that one I'm calling signal, the second photon I'm calling idler. If I detect the signal photon, and here I'm making polarization measurement, of course. So if I detect the signal photon to be horizontally polarized, what I find that the idler photon is guaranteed to be horizontally polarized. At the same time, if I find the signal photon to be vertically polarized, idler is also guaranteed to be vertically polarized. Now the question is, which theory can explain this? So let's try quantum mechanics, wave function. So if I have this kind of state, it can actually explain this measurement outcome. This is HH plus VV. So of course, if first photon is H, second is H, first is V, second is V, and so on. Can a hidden variable theory do it with two independent sources? Yes, it actually can. So what do we have? So this source here, and we'll have few rules. What are those rules? The rules are both sources emit simultaneously and emit the same polarization. That means if this emits H, this also has to emit H. This emits V, this also has to emit the same thing. So both sources emit simultaneously and same polarization. 50% of the time, both sources emit horizontally. 50% of the time, both sources emit vertical. Like this is probabilistic. It's not that the first fire is both horizontal, second fire is both vertical, nothing like this. Like completely random as to when they fire what. But whenever it fires vertical, it also has to fire vertical, and same for the horizontal. And if I fire it 10,000 times, 5,000 is vertical, 5,000 is horizontal. If we have these two independent sources of these rules, then I can also explain this measurement outcome. So then is this situation entanglement? Answer is no. The second situation, the measurement outcome is if I get the signal photon to be 45-degree polarized, idler is 45, signal is minus 45, idler is also minus 45. And in this case, a wave function like this can actually do. And also if I have the hidden variable model, the same thing in the 45-degree can also do it. Is this entanglement? No. Third measurement results. Here what I have is whenever I measure signal to be horizontal, idler is horizontal. Whenever signal is vertical, idler is vertical. At the same time, whenever signal is 45, idler is 45, signal is minus 45, idler is minus 45. Can I explain it quantum mechanically? Yes. This is the state that I can actually do it. Why? Because if this is state, H2 basis transformation can be written like this. So here it explain this HHVV connection. Here it will explain 45, 45, minus 45, minus 45 correlation. But now can I make a set of rules between two independent sources such that it can still explain this measurement outcome? So this was the challenge accepted by the people who are making hidden variable theories. And it turns out that one cannot actually do it. It is impossible. And so is this entanglement? Yes. So whenever we have correlation, at least in polarization basis, if we have simultaneous correlation between in the HV as well as in 45 minus 45 basis, that's when you can say it is entanglement in the discrete variables. So there was a lot of effort in the 1935 to 1960s to make these kind of theories. Didn't work. And then, well, people kept actually doing it. Then in 1964, we have Bell's inequality, and Bell actually proposed a test. And if that could be violated, that means quantum mechanics is actually correct. Then it was shown that yes, Bell inequality can be violated, and which essentially means that one cannot have a hidden variable interpretation of quantum mechanics. And last year, 2022, there was a Nobel Prize given for this, which actually almost puts a stamp that you cannot have a hidden variable interpretation of the measurement results that you get. Quantum mechanics is the only theory that can explain all the measurement outcomes that one sees in the lab. Okay, so now we talked about entanglement, something on, what are the sources that can actually produce it. Maybe I can, in the interest of time, I can skip it. So one source, at least in optics, that we have is called parametric down conversion. This happens in nonlinear crystal. One photon gets absorbed by the crystal, and in turn, two photons come out. Of course, you have to satisfy the momentum and energy conservations and so on. And these two photons that actually come out, these are entangled in various degrees of freedom. So I don't want to go into the details of this, but if you're interested, you can. I have written a very tutorial article. This has all the details. And if you just want to play with this, we have developed a web app. If you go on to my website, so this is the web app, if you can see it. Here you can just simulate different conditions. For example, this is type 1 that I'm doing. This is for the BBO crystal. If you change the phase matching angle of the BBO crystal, for example, if I do 29 point, let's say 45 here. Probably have to refresh it. Right. So this is one. Let me just change it to. Right. So if you want, you can just play with it. This just gives a very nice intuitive way of understanding. This is the crystal thickness that I'm using. Change the crystal and things will change. Reducing crystal decreases the thickness. If I increase the crystal thickness, it'll just reduce, make it very, very sharp and so on. So you can actually play with it. So so this is that is a source. I didn't talk in much detail. So these are all the entanglement, all the different types of entanglement one can have, and of course there are several applications: quantum computation, quantum communication, lithography, cryptography, teleportation, imaging, and so on. Maybe one of a few applications that I can talk is quantum lithography, or if there is question, maybe I can even stop here because I think it's 45 minutes. So if there are questions I can take, or if you want, I can continue.
No, please continue. Please continue. This is very interesting. Yes.
Quantum lithography, this is actually just based on one weird effect that one gets out of this entangled photon. So for example, I have these two photons produced here. If you mix them in a beam splitter, then there are four possible ways that these photons can actually get out. But if you set this condition right here, it turns out you can get rid of these two alternatives, and you end up with just these two. So that means if these path lengths are exactly equal, then both the photons either go this way or go that way. And so if you're looking at the joint probability of these two photons arriving in the detector, what you find is when x equal to 0, this coincidence is 0. That means both the photons either go this way or go that way. Now, this fact can be used for lithography. How? So the conventional lithography or the classical lithography works like that. You have a beam of light, although I'm doing it with one photon, but you have a beam of light. So part of it goes this way, part of it goes this way. You combine them at a substrate at some angle theta. Theta is usually almost 90 degrees. And with that, you can see that the intensity here is 1 plus cosine 4 pi x by lambda, where lambda is the wavelength. And if you plot, it looks like this. Fantastic. Now, if I can bring such a source here, so that one photon comes this way, one photon comes that way, such that I have two going this way, two going that way, same setup. Now, if I calculate the coincidence intensity here on the substrate, I get 1 plus cosine 8 pi x by lambda. Now, the point to note is the lambda is same for one photon or classical or two photon. So same lambda, but now I'm getting a higher resolution. So if I now plot it, I can write twice as many fringes I could do earlier with the same wavelength. So in semiconductor industry, if you want to write finer pattern, you have to reduce the wavelength. But if you use entanglement, you're not reducing the wavelength, it's the same wavelength. Use two entangled photons, you can have twice as many fringes. And if you have n entangled photons, you can actually reduce the fringes by a factor of n. So that is the whole idea of quantum lithography, that is n-fold lithographic resolution enhancement. The other is induced coherence. I can maybe go very quickly. These are some very weird counterintuitive applications of quantum entanglement. Here in this application, the object was kept, let's say you have entangled photon, this yellow and red. Object is kept in the path of the red, but the detection is done only for this yellow. No, you're not detecting this red light. But through the detecting only the yellow, one can actually image the object that is over there. So this is a different wavelength, that is a different wavelength. So you're not even detecting the photons that actually saw the object, but you can still see the image. That's very weird, can have a lot of application, but this is one of the things that you can get from quantum entanglement. Quantum cryptography, I think quantum cryptography, many of you know already, so this part I will skip. But one thing I need to mention, the quantum cryptography in 2017, it has been shown, from the satellite to ground to satellite scale, it has actually been demonstrated. Not the full security, but the basic has actually been demonstrated. You also have quantum teleportation. Quantum teleportation, one tries to send the state, not the quantum, not the system, but to send the state from one point to the other. So the example that I have is usually you can't send the person, but you can send the smile, and that is what is meant by teleportation. So some of the results that we have in my own lab, So actually, I'm done with the background. Again, I will not be talking too much of my own lab, but we have been working on, measurement schemes for making better and better kind of measurement scheme for measuring the quantum state of single and entangled photon in the orbital angular momentum basis. And in this work, we actually showed that with just two measurement, one can actually measure quantum state up to 85 dimensional state. In addition, we also working on classical quantum techniques for increasing the resolution of images, especially in the scattering and turbulent media. In this work, we actually showed a new measurement technique in which the two photon entanglement, position momentum entanglement, can actually be done with just doing single photon detection. And we reported the best EPR violation, reported so far. So this came out last year, and very recently, this is for the first time we have shown that entanglement can actually be revived through just propagation, and this entanglement revival happens even in the presence of turbulence. So this was last year. So a few things in the lab. This is how a real optics lab, kind of quantum optics lab, looks like. These are the real people in the lab. And finally, let me thank the funding agency for some of the things that I've shown, IIT Kanpur, DST SERB, and DST Quest also. If you have any questions, this is my website. I put in a lot of stuff there, but anybody interested in getting in touch for more information or looking for position, PhD, postdoc, please do get in touch. And finally, thank you for your attention. I can take a question now if anybody has.
I have two questions. So thank you for your presentation. So how do you create LG modes by using SLM or in a resonator?
I create using SLM.
Okay. And the second question is for my clarification. So in one of, if I understood correctly, in one of your slides, you were saying that we see Fourier transformation on the screen. So does it mean that Fourier transformation of the wave function will provide coefficients before cosine and sine functions, and cosines and sines are orthogonal to each other? It means that module square of coefficients provide position and intensity value on the screen. Am I correct?
Yes.
Okay, thank you.
So ultimately, because you're right, because ultimately what I'm getting is the intensity pattern. So yes, when I'm saying Fourier transform, it is a complex pattern that we are putting here. So so phase and amplitude both, it needs to be specified as at the SLM, such that the intensity pattern, the far field, is what we want. Correct.
Okay. Thank you.
Okay.
I can see one question in the chat, which is from Ritvija. So I can take that. So it's like, can we break the entanglement between two parties by changing their basis? Is entanglement between two parties frame dependent or universal? What do you mean by frame dependent? If you can, I'm sorry, I didn't get the question. Hello. This is from Ritvija.
Right. We don't see her writing anything.
Okay, fine. Maybe this wasn't my chat, but that's why I can take other questions then. Okay.
Right. I have a question, a very short one, is basically in the last slide, you were talking about the entanglement revival, some experiments. Can you elaborate that a bit?
Okay, so this I did in just 30 seconds. So this is a recent result that we have actually found. This is for the entanglement generated from BBO crystal or nonlinear crystal. So typically, if you, I mean, these photons are usually entangled in more than one basis. That means time, energy, position, momentum, polarization, angular orbital angular momentum, so on. But in the continuous variable, for the CV entanglement in position momentum basis, what happens is that these two photons are generated, and if I'm looking at the position momentum entanglement, they actually get lost after a centimeter. So after a centimeter, if you do the EPR measurement, you will not see it by violating the Heisenberg bound.
I see.
But what we found that without doing anything, literally anything, what we found that if I look at the entanglement not in the position momentum basis, but in the angular orbital angular momentum basis, what we find that entanglement just upon propagation definitely gets lost after a while, and that too again about a centimeter. And if for the regular kind of crystal size, this 1 centimeter is no holy number. It is just based on what are the parameters. But then it gets lost. But then after a while, it actually revives. It comes back. And once it revives, it stays forever. Forever meaning for any propagation distance, as long as the trace is preserved, as long as I'm detecting the whole system, the entanglement stays intact. So this is what we actually see experimentally, that this is the delta X, delta L product. You see, this is becoming larger than 0.5 H bar upon some propagation. So you can say it is entangled up to here. Now entanglement lost, but let's say at Z equal to 24 centimeter, it actually comes back and then stays entangled. So then what we said, okay, fine. Now this is us without us doing anything, that entanglement device, that's very nice. But let's say if we introduce some turbulence, that means if you make the entanglement even worse, that or degrade it even further, does the system revives,
How do you introduce turbulence? I mean, you apply fields?
Yes, no, not fluids, but so this is still real turbulence. This is what we were using is the blower heater that we use in for just like room heater, but a very portable version of that. So a room heater, and that we blow just hot air, and this experiment actually takes about 8 hours. So yeah, for 8 hours we were like blowing air, and that introduces turbulence. And by controlling the speed of that air, we can actually control the strength of turbulence to some extent. But here I have a result only for one turbulence strength. So of course here, since we're putting the blower heater, I don't have any result before that. But after that, you see even after turbulence, the entanglement does revive. But the revival that was happening before turbulence at Z equal to 24, now the revival is happening at Z equal to 35. So the only effect of turbulence seems that if you have turbulence in the system, but you still want to have entanglement, just kind of propagate a little bit further, and entanglement kind of comes back.
I see. It's very nice. It's very interesting. In the meantime, thank you. I mean, I got the answer. And then I think Ritija, she explained what she means. So she has written in the chat that, sir, by frame dependence, I was trying to mean if we change the basis states, or is quantum correlation holds in all the basis states equally?
Okay. So now I think I understand her question. So quantum entanglement, as we understand, is not something very intrinsic. It is a basis dependent quantity. So when I say entanglement, this is an incomplete statement. I have to be more specific that entanglement of signal idler photon in the polarization degree of freedom, or entanglement of these two photons in the position momentum degree of freedom. So, and if I say, whenever I say entanglement in position momentum degree of freedom, that means then it has to be that they are correlated in position as well as in the momentum basis. Or when I'm talking about the polarization, I will have to bring two separate bases. One basis for polarization that I was talking about is a horizontal vertical. The other one could be 45 minus 45. So if you have a pair of conjugate bases, and if you find that the pair of photons are showing correlation in both the conjugate bases, then only we say or claim that we have entanglement in that particular degree of freedom or in that particular basis. So that's how it is actually understood. If we change the definition of basis or basis, then it will be a completely, these are uncorrelated things. If I change the basis, that completely changes the definition itself.
So I have a question, sir. So why here? How can we explain this revival of this entanglement? Like once it is lost, but how do you explain?
Okay, I understand your confusion. So it's like these are all unitary transformations. So why, if we are not changing anything, why does entanglement change, right? So again, this is connected to what Rituja was asking. So entanglement, as we understand it, it's not necessarily in a very, it is, current definitions are all kind of basis dependent definitions. But still, what we have is definitely all unitary transformations. Even when we have turbulence, this can still be modeled as a dynamic system, but to some extent it's still unitary. But what is happening here is that this is just one way of looking at entanglement. That means I'm looking at entanglement in the position and momentum, angle, orbital angular momentum basis. Now, in the angular orbital angular momentum basis, I find that this is the dynamics of entanglement. That means it kind of when I say get lost, I basically mean that this matrix that I have is not able to capture entanglement. That this matrix is not able to confirm whether there is entanglement or not. But that does not mean that the entanglement by itself is not there. Maybe it is there, but the lens or the camera or the matrix or the that I'm using to actually verify that the same matrix which is working here is no longer working. So that's why I'm saying the angular orbital angular momentum entanglement, that is not there here in this range, and then it comes back over here. And so maybe in this regime, it has gone on to some other variable, maybe position momentum, maybe some other. And so if we can find all the different possibilities that this entanglement can go to, and then if we sum them up, maybe linearly or in some functional form, maybe then we find that we get a quantity that is actually conserved. But what we have is looking at entanglement in the angle orbital angular momentum basis through EPR criterion.
Okay. Thank you so much.
Do we have other questions?
Can I ask one more question? Or
yes,
like
please.
a clarification. So you were talking about the room heater. So what kind of loss mechanisms can we expect from the room heater? From my point of view, particles of the heater are moving randomly, and as a result, refractive index of room heater particles change the direction of photons and polarization. Maybe please, maybe I'm wrong, please correct me, or maybe some other effects we need to consider also.
No, you are absolutely correct. But here I'm not taking the loss into account, but you are absolutely correct. This heater is there, but it's not producing very strong turbulence, but to whatever extent it's producing turbulence, these things are random, and there will be some loss. But let's say again, if you see my fit, this is my theory, which assumes no loss from the heater, but it has a model for turbulence, and this is my experimental result. So when I have no turbulence, this fit is pretty good, but when I have turbulence, it is not that good. So those factors are definitely here. Those factors are definitely here. But even with the losses and stuff that are there, the only point here is that I'm able to cross this line. Now, if you see, theoretically, I'm supposed to cross it 35 centimeters, but experimentally, we actually cross it around 48 or something centimeters. So the effect of loss is there, but we didn't incorporate that in this work at least.
Okay, thank you. Maybe one more question. Why you are using OAM light, orbital angular momentum light, as compared to plane waves or Gaussian waves?
Okay, right. So, well, I just didn't do any background as to regarding my own work. So, orbital angular momentum actually provides a very nice basis for quantum technologies. So like plane waves are kind of difficult to. Plane waves are not a very comfortable basis to kind of work in. They are also a basis, but plane waves are not a very comfortable basis they are also continuous. So making a detector is kind of, everything is difficult. But for OAM, the one good thing, that one advantage that we have over the plane wave type of basis is that it is discrete. It is not continuous. But when you have discrete basis, that's what people would prefer for quantum computation, quantum cryptography, and so on. And that's why everybody wants to kind of work with the OAM basis. So that probably is the one main reason. Plane waves are very good when we want to explain, some concept, and in the quantum books, everything is done in terms of plane waves. But experimentally, those are very difficult to work with.
Okay. And what about the diffraction? So, do we have big impact when the wave propagates in the atmosphere?
Absolutely.
Due to the diffraction?
Okay. Absolutely. I don't have those simulations here, but you're absolutely correct. So of course, whether it is plane wave or OAM or any, if it's a wave, there will be diffraction. So what in fact, if you see here, the beam, the way I'm plotting the beam is thin here and it kind of becomes bigger and bigger. So, and again, I was saying that this entanglement, once it actually comes back, it stays intact. It doesn't decay any further. But this was with the assumption that the diffraction is not as big, the divergence to diffraction is not as big, that it goes out of my collecting lenses. So as long as diffraction is such that I still capture the whole field, then this effect will actually be there. But now if the diffraction is so much, these experiments are done over like a meter, but let's say I do the same thing over 10 meters, then diffraction will be more, and I cannot capture that with the 1-inch lenses that I'm using. But if I doing the experiment at 10 meters or 100 meters, but if I have sufficiently large lens that it captures the whole field such that the trace is preserved, then this effect actually continues. So the diffraction effect fundamentally are not changing anything, but as long as we collect the entire field.
Thank you.
Thank you, Professor Jha, for answering the question, taking the question and answering them. Thank you for your time, and it's a beautiful presentation.
Thank you.
So maybe we bring the session to a close. Thank you very much again.
Thank you.
Thank you.
Kind attention for the participants, and there will be a quantum optics tutorial from 3 to 5 p.m. So it will be completely pedagogical. So please tune in, and it will be a lot beneficial for you all. Thank you.
Who is going to deliver this training?
It will be given by Subhasis Barik. He is from QIQT Labs. So yeah, that.
Okay, thank you.
Yeah.